All right, so it looks like I've already got a question in the chat, and someone oddly liked this stream before it started. That's rather ambitious. So the question is regarding the lab. I'm assuming based on the question that this is the rates of reaction lab, and it asks, when it tells you the data analysis, it tells you to compare one run to the previous run and not run to the base run. So I'm guessing based on the question, so you've got two reactants, A and B, and you've got some concentration. I'll just 1, 1, 2, 1, 2, 2, 1, 2, 3, 4. And so just kind of based off the context of the question, what I'm guessing is that what it's trying to do is it's trying to make you compare runs where only one concentration is changing. So we have the apparent formula, the apparent order natural log of one rate over the other equals the apparent order of one reagent, its concentrations at the two different runs, plus the other reagent, its concentrations on those two runs. So to kind of base what I saw skimming over the lab worksheet, this base run 1 and 1, I'm just making up the concentrations. I didn't work out what they were. My guess is that if you compare this, you consider this your base run, and you do compare the third run to the first run, two concentrations are changing now. Now it is possible to solve this equation because if you compare the first and second reactions, you'll get the order of one of the compounds and you can just stick that in. But for simplicity, you'd rather just compare two runs where only one concentration is changing. So again, my basing on the question that's being asked, I would say the reason it's asking you to compare it to the previous run and not the first run is because if you compare it to the first run, both concentrations of reagents are changing, whereas you compare it to the previous run, only one of the concentrations is changing. And again, you don't have to do that. If you've already compared two runs and you got the apparent order of one, you can just stick that into your equation now and you can just keep working with it as is. It just simplifies your life a lot if you compare runs where one concentration is being held constant and the other one is being changed. And ideally in a more robust course, what you would actually do is use a nonlinear solver and just compare all the runs at once because there is experimental noise. And I tell students on exams it's kind of nice because we give you the really idealized data, so you always get like that beautiful integer that like pops out like 1.00, 1.01, or 0.99. In the real world, you're probably going to get fractional orders. So any questions out there? Yeah, it's actually answered at the start. So it is interesting. It'll actually show me the post in advance. So I was going to do is respond to somebody asked me something in a different stream. Oh dear. But yeah, to answer your question, I think the reason why it's telling you to compare it to the previous is that it wants you to compare two runs where only one concentration is changing. If you compare it to the first run, then you may have two concentrations changing at once. You can definitely work with that. It's just a lot easier if you just rely on one concentration changing. Yeah, I'd recommend doing the distilled water if you can. I had a student email me this morning, and they're having issues with the copper catalyst. And I think because they're using tap water, there's just peroxide and there's iron present, which is causing the reaction to go forward. Um, Nature of home experiments. The copper catalyst is cool. You will see it actually catalyze the reaction, like they go super fast. When we do it physically and seed it, it takes about 70 to 80% of the time off the reaction. So it is really cool. As instructors, our concern for students are actually the learning curve when y'all get back to the labs, because particularly with organic, we only do the hybrid sections. We don't do we don't have an online version of this class, just hybrid. And we definitely see that with students who've been online for Chem 1 and Chem 2. Like, they genuinely have never had to work in a lab before, so they don't really like know how to work with the classroom. There's a steep learning curve. I should do this when I'm feeling more motivated. I need to make exams for the fall. No, just go with whatever you can, and that's just inherently built into the errors of your analysis. So, yeah, if you add it and there's like a little bit of a lag, that's just the nature of the experiment. I wouldn't worry too much about it. You're not doing precise science here. What you're trying to do is just get more of the experience of collecting the data and doing the analysis. Um, Perfecting the technique is something that would more be done if you would just do the process over and over and over again. So when we do organic, there's a lot of techniques that we recycle over and over again. So when we do organic, what we're trying to do is we're trying to teach you how to do the techniques in addition to understanding the theory. And so a lot of the labs, you'll see a lot of the same techniques show up over and over again. There's thin layer chromatography, separatory funnels, things like that. Those we start worrying more about you doing it precisely and doing it accurately. Again, here you're more trying to see the application of the theory. No one's expecting you to do it with the precision of an expert. Because the other thing, these are all home lab kits. Like you're using eyedroppers. Like there's only so much like precision we can expect. through the first problem of test 2, pre-exponential factors and EA homework. All right, so let me bring up the homework then. A little bit of a slow computer. Okay, so for this homework, you're going to need to download the homework that is on the course website. So if you go to the lessons folder, and you're going to find 2 assignments. One says for the EA and pre-exponential factors, the other says for concentration versus time. This is going to be the one that is, the file itself is called K versus temperature. So what we have to do is we have to use an Arrhenius plot. An Arrhenius plot, we have that K equals A to the E to the minus EA over RT. So we're going to linearize this, and we get that the ln of K equals the ln of the pre-exponential factor plus minus EA over R times 1 over temperature. The ln of K here is going to be our Y values. The 1 over temperature is going to be our X values. This means our slope is minus EA over R. And our y-intercept, B, is the ln of the pre-exponential. So if we rearrange this, the pre-exponential is just e to the y-intercepts. And here, our activation energy, EA, is minus R times the slope. Make sure you can see that. So yeah, we're going to have to plot ln of K versus 1 over temperature. We're going to put in a linear regression. We're going to take our y-intercept, raise e to that power of the y-intercept, and define our activation barrier. We're going to take our slope and multiply it by negative R. So on the homework, the first one is, where are you? To 3 significant figures to determine the pre-exponential factor A and the activation barrier for case 5. So if I bring up the homework, I'll show it to you on my end. So we need 2 things. We need 1 over temperature. That's our X. And we need ln of K is our Y. I'll try to make this a little bit bigger for you. So to find 1 over temperature, it's 1 divided by, and we need to convert the temperature to Kelvin here, so plus 273. And we need the natural log of the rate constant. So if I insert a scatter plot, give a linear regression, and what I'm going to want to do is display the equation on the chart. All right, so I get my y-intercept B and my slope. So my y-intercept here is 8.4471, and my slope is minus 6527.6. We're almost out of Excel, almost. So our A, our pre-exponential factor, is going to be e to the b power, and my EA is going to be minus R times the slope. So A here is going to be the exponential, and the EA here is going to be negative 0.008314 times the slope, so 54.2. So I can bring this up, and it already kind of shows you here on my end. 4660, it tells you to do 3 significant figures. This is just to simplify your life. So it's 4660, and your EA is 54.3. And you're just going to repeat that over and over and over. So honestly, if you just copy and paste the data from the other ones, you can automatically get that like to update for you. But yeah, to find the activation barrier, you have to use an Arrhenius plot. It has to be used across the different temperatures. These are actually like real world things. Like I've had to do the Arrhenius plots for different catalysts before to figure out their EAs. EA is a much better measure of a catalyst performance. Because your catalyst might perform poorly, but that may just because you didn't, utilize it very well. The activation barrier itself is endemic to how fast the reaction can go. Other questions out there? Tomorrow. Today's Thursday. There's no live stream tomorrow. But yeah, come back Monday. We only do Monday through Thursdays in the summer. Officially, we are closed on Fridays. Also, apparently tomorrow's a federal holiday now, Juneteenth. But Yeah, in the summer we only do Monday through Thursday. Although I do try to answer emails in the weekend, definitely not very quickly. Usually like first thing in the morning and right kind of in the afternoon. Any other questions out there? Yeah, 30 minutes left. I guess I could work on the exams. Not your exams, the exams for organic. Just a minute. Need to clip one thing about this picture. Oh my goodness, the mouse in this computer is just off. Having trouble understanding the formula where LO isn't anything to the zero. So the zero here actually refers to the time. So it's an A sub zero. We'll sometimes refer to this as a naught. And it just means that time equals zero. So the way mathematicians like to write it is any function. This means evaluate at t equals t0, t equals 0. We just shorthand that by saying a naught or a sub 0. But it's a subscript and not a superscript. Now, if we had a superscript, yes, you would be correct. If we raised a to the 0 power, that would be 1. Correct. And it's not temperature, it's time. So we have Ln concentration of A equals Ln A naught minus KT. The T here is time. So little t is always time. And big T is temp. And pretty much from here on out, we're going to be working in Kelvin. So this isn't 0. So the natural log of any number greater than 0 is always going to be, I shouldn't say bigger than 0. It will never be 0. Well, unless it's 1. Okay. I was wrong on that. But that term isn't always 0. It's whatever the natural log of the starting concentration is. Now, if your starting concentration is 1, the ln of that is going to be 0. So our starting equation is the concentration of A. Is the starting concentration e to the minus kt. So A here is our concentration at time. A naught is our starting concentration. K is our rate constant. And T here is time. So what we can do is we can rearrange this equation, Excel sheet. So if you're looking at the one for the rate constant K, that doesn't use concentrations. That uses K as a rate constant in temperature. This is for the concentration versus time Excel sheet. So we can linearize this if we take the natural log of both sides. We get the natural log of all this mess. There's a property of natural logs that says that if two things are multiplied together, we can just add them, add their natural logs separately. And the natural log of any number raised to the e is just that number. So that's where this equation comes from. Now there is another homework assignment that is the concentration versus time. So that's this worksheet here. And for this one, you need to do 3 plots. You need to do the natural log of concentration versus time. And you need to do 1 over concentration versus time. And let me throw a trim line on that. So these are the plots you're trying to generate for that homework. You've got, I know it's going to be a little hard to see on your end, concentration versus time, the natural log of concentration versus time, and 1 over the concentration versus time. So in these, you are giving concentrations and you're trying to create these plots. Yes, I know I can click other windows. It's fine. So again, you're trying to quote 2 plots that are not the same thing. So when we're looking at K and temperature, we're looking at an Arrhenius plot. We're not looking at this equation. This is for concentration versus time kinetics. The Arrhenius plot does not concern itself. So the A here is not in brackets, and I think that's where the confusion is coming from. So that is not the same thing as that. Brackets here refer to concentration and molarity. A here is a pre-exponential. And the problem is there aren't any good letters to throw in there. So if you're wondering why we're constantly using A, it's just because we don't have options. If we put C as a pre-exponential, it'll look like concentration. If we put B, it'll look like one of our reactions. If we use an E, it'll get conflated with the E beside it. If you use D, like, it doesn't matter what variable you throw in there. So the A here in this equation is not concentration. Concentration has brackets around it to designate that it's concentration. So that's our shorthand to designate whether A is a variable or A is a concentration. test. Correct one thing. God, I hate the mouse on this computer. Can you go through the first problem of creation again more slowly? Okay, so let me bring back up the homework again. And again, what we're going to do is we're going to try to fit to the Arrhenius model. So the Arrhenius model here says that the natural log of our rate constant k, which is going to be the y in our graph, is equal to the natural log of the pre-exponential factor minus EA over R times 1 over temperature, where 1 over temperature here is going to be our x. So this will give us two things out of the graph. The y-intercept numerically is the natural log of the pre-exponential, so our pre-exponential is just e to the b. And our slope is equal to minus EA over R, and so our EA here, if we just rearrange this, is minus R times the numerical value of the slope. So the way we do this practically in the lab is that we go through the lab and we actually measure it. So at one temperature, we measure the rate constant. We go to a higher temperature, measure it, higher temperature, measure it, and so forth. Now this would be a very, very nice set of data. But we want an Arrhenius plot, so we need to have our x, which is 1 over temperature. And we need to have our y, which is the ln of k. And the temperature here has to be in Kelvin. So here we've got our tables of x's and we've got our tables of y. And again, the reason we're doing this is we're going to create a plot where we've got y and x values, and we're going to stick a linear regression in it to extract out a slope and a y-intercept. So if I insert the plot, I get my slope, my y-intercept, my slope is minus 6527.6, and my y-intercept is 8.4471. Now we also know from the board behind me that the numerical value of the slope equals the natural log of A, and the slope equals minus EA over R. So I'm going to put those in the sheet just for illustrative purposes. So this is also going to equal minus EA over R. Nobody cares. And the y-intercept is going to be the ln of our pre-exponential. So to solve for EA, our activation barrier, we just rearrange this equation. M equals minus EA over R, so EA equals minus R times M. And for our pre-exponential, A is going to be e to the b. So that's what we're doing with these plots is we're taking our measured data, our rate constant K, our temperature in centigrade, we're converting it into an Arrhenius plot, which is the natural log of K versus 1 over the temperature in Kelvin, using that plot to extract out a slope and a y-intercept, which by theory, the numerical value of the slope should equal minus E over R, and the numerical value of the y-intercept should equal the natural log of the starting concentration, and doing some algebraic rearrangement to get back to the EA and the pre-exponential factor. All values in column D. So are you using ln of K itself, or are you using the ln of 1 over T? So the ln of k is the ln of the rate constant. So when it says, you got the column that says rate constant 1 over minutes, that rate constant is k. So A2 is just the ln of k. K is not in any units of Kelvin. So k is in units of inverse minutes for this particular problem, but it's just literally the ln of the rate constant. The 273 correction factor is for the temperature because the temperature has to be in Kelvin. So for your C column, the x is 1 over temperature plus 273, simply because we have to be working in Kelvin because of that ideal gas constant R. But you don't add 273 to the rate constant. There's no physical meaning to that. Yeah. And if you still got questions, come back Monday. The exam isn't until next week, so you still got time. Yeah, you're welcome. Homeworks aren't necessarily in order of difficulty. So I have not really found a good way to control the order in which it presents to you the assignments. So you may actually find that a lot of the homeworks, like especially the things that are like how to do apparent, how to find like the orders from the reactions, what are the intermediates, those actually go really fast. So if you're doing like the concentration versus time, the ones that require the Excel sheets, those actually take the longest time to do. But it's also a 2 week course. It's also an abbreviated course. It's 8 week versus 2 weeks. So we are doing double pace here. All right. So thanks for showing up. Live stream is Monday again. Tomorrow we don't ever have classes on Fridays or live streams on Fridays. So I will see y'all next week.